Volleyball is going to be leaving a little early today, I believe, so I'm going to make sure we get started and hopefully we can get through some punching this week. So. All right. So we got into chapter 8, covalent bonding. We got through section 1. Section 2 is naming them. Okay, so we have another set of rules. Yeah. So we have another set of rules that we need to go over. We're going to go over them pretty quickly because I don't want to emphasize naming. That's just not what I feel is the best use of our time. But anyway, now we're going to work through, well, let's just read the rules first. So these are on page 248. Number 1, the first element in the formula is always named first using the entire element name. The second element in the formula is named using its root and adding the suffix IDE. Okay. And number 3, prefixes are used to indicate the number of atoms of each element that are present in the compound. So this is honestly the biggest difference between covalent and ionic bonding names. In ionic bonding, we didn't care how many of each thing there were, okay? So if we, for instance, in ionic, had that, we just said magnesium chloride. It didn't matter that there were 2 chlorines. But when we have a covalent bond, it does matter in the name. And honestly, the biggest reason for that is because in ionic, you can figure out what the ratios are, okay? Because they have to be evenly charged with positive and negative. We don't have that same rule with covalent, so we need to say how many of each there are. So as we're looking through the rules, it uses the example N2O. So rule number 1, the first element in the formula is always named first using the entire element name. So we have nitrogen. Okay. The second element in the formula is named using its root and adding the suffix IDE. So oxygen, the root is ox, oxide. Okay. And then 3, like we said, this is where it gets different. Prefixes are used to indicate the number of atoms of each element that are present. So we look at this table 3, and it gives us 1 through 10 of the different prefixes. 1, mono, 2, di, 3, tri, 4, tetra, penta, hexa, hepta, octa, nona, deca. So, how many nitrogen atoms are there? 2. What's the prefix for 2? Di, di. So it is dinitrogen. And what is the prefix for 1 oxygen? Mono. Now we do eliminate the O. We don't want double O's just because that's kind of awkward to say. So we don't say monooxide. We eliminate one of them and just say monoxide. So that is dinitrogen monoxide. There are more examples. We'll do one more here. So Okay, rule number 1, first element, phosphorus. And then, once again, you have oxide. Okay. How many phosphorus do we have? 2. 2, so it's diphosphorus. How many oxygen? Pentaoxide. Now, once again, having 2 vowels next to each other is a little bit awkward. So we will typically drop one off. So, pentoxide.
Oh, so you don't need an A?
No, if you have 2 vowels back to back,
Oh,
it's just kind of awkward to say that. So we drop off the one in the prefix. Okay. Like I said, I'm not going to really harp on the names. As we go through class and we use them more, you'll probably get more comfortable with them. But yeah. But that should tell you, so carbon dioxide. You should be able to use that name and tell me what's the formula. CO2, carbon dioxide. Okay. Now, one exception to the rule is right there. We don't say monocarbon. Okay. If it's the first thing in the name and there's only one of them, we just leave off the mono. Okay. So carbon 2 dioxide. This is technically 2 vowels together, but I and O are okay. Just not A or double O. But yeah, this is another reason why I'm not going to harp on naming, is because there's all these weird exceptions and things like that. So we give you the rules, and we say, but this one doesn't follow the rule, and neither does that one, and blah, blah, blah. So, like I said, as you go through chemistry, you'll get a little bit more comfortable with how these work until eventually it just kind of becomes easy. The book does point out some things do have common names, like this. So nitrogen trihydride, we just call it ammonia. Okay. So plenty of things have common names, but like I said, it takes a little bit of practice and work figuring out where these common names are. So once again, we're not going to really focus too much on naming. For acids, there are some specific rules. For binary acids, that means you have hydrogen and something else, like chlorine. The way we name that, we start with hydro for hydrogen. We add the root of the other one. We add an IC, and then acid. Okay, hydrochloric acid. And then oxyacids. Once again, just like the polyatomic ions, I'm not going to expect you to memorize the oxy ions names. Just look them up. Okay, if you ever run into them on homework or whatever, just look them up. So, anyway, that's naming. Like I said, I want you to be aware of it, do a little bit of practice with it here and there. But I'm more concerned about some stuff that we want to talk about now. Let's move into section 3. So section 3, getting into molecular structures. We want to know the shapes of these different molecules. Okay. We want to know the shapes. And obviously, we can't just use a microscope, especially, back in the day. So we had to come up with some other ways of determining these and representing them. Okay. So if you look at page 253, you can see 5 different ways that we can represent different molecules. Now this one happens to be phosphorus trihydrate, okay, which does have a common name, phosphine. Okay. Gives us the molecular formula, which is super easy. Okay, we just write CH3. That's easy. We also can draw a Lewis structure. And now remember, we talked about those. So phosphorus, if we look at our periodic table, is in group 15. Group 15 has how many valence electrons? 5. So we're going to start with 1, 2, 3, 4, 5. And look at that. We have 3 spots where a hydrogen would fit perfectly. Now sometimes, and this is the case in the book, they will represent these bonds as lines. Just understand that those are the same thing. Okay? Same thing. I don't care which one you use, as long as you understand that this line, this bond, means that there are 2 electrons being shared. Okay. It goes on to what's called the structural formula, which is essentially the same as the Lewis structure. It just omits the extra electron pairs. Okay, so pretty much the same thing. The other 2 I'm not going to try and draw on the board because, well, you can look at them and see why. We've got the space filling model and the ball and stick molecular model. Those 2 show a little bit more of really what it looks like in 3 dimensions. So, when we draw Lewis structures, okay, sometimes it takes a little bit of practice to figure out exactly how we need to do them. Once you get that practice, once you do it a little bit, Lewis structures actually become really easy. But it is going to take a little bit of practice. Okay. Until then, we have this lovely outline of 6 rules on page 254 that will help you. Number 1, predict the location of certain atoms. So you just want to sort of predict how things are going to be. Okay. And it gives a little bit of hints here. The atom that has the least attraction for shared electrons will be the central atom in the molecule. This element is usually the one closer to the left side of the periodic table. Okay. Obviously not in this case because hydrogen is as far left as you can get, but if you are not dealing with hydrogen, then yeah. And then everything else kind of goes around that. One trick, if there's only one thing with a bunch of hydrogens, that one thing is going to be in the middle. Okay? So if there's one thing with a bunch of hydrogen, the one thing will be in the middle. To determine the number of electrons available for bonding, we did that when we were drawing Lewis structures before. Remember, you count up how many valence electrons everything has, and at the end of the structure, that's how many electrons you need to have. You can't have more or less. Determine the number of bonding pairs. Well, since these bonds are pairs of electrons, take the total number of electrons divided by 2. Okay, that's how many bonds that you are going to make. Place bonding pairs. Start with just doing a single bond between the central atom and everything else. And then how many do you have left over? Sometimes you may not have any left over, but sometimes you do. If you have any left over, fill them in where you need more electrons. Just putting a single bond around everything will not necessarily give you the correct amount of electrons for the octet rule. So make double and triple bonds. And then finally determine whether or not you need to have lone pairs of electrons to that. So we worked with Lewis structures last time. And like I said, it's going to take a little bit of practice. Maybe we have some practice. Pretty sure I assigned some practice in the homework. Let me just look. Yep, there's some practice. So if you're having issues with Lewis structures, like I said, give it a try and then come see me, okay? So we can figure out where you're struggling so that we can make sure that you're getting this. It also goes through polyatomic ions, drawing Lewis structures. Basically, it's the same, except you have to account for extra or missing electrons because it's an ion. Okay, that's really the only difference. You have extra or missing electrons because it's an ion. So if you ever have to draw the Lewis structure for an ion, just keep that in mind, okay? You need to account for those extra, most likely it's going to be extra electrons. So, okay. Resonance structures. Resonance structures are Lewis structures. Now, when you hear the word resonance in chemistry, you automatically know we're dealing with double bonds. Okay? If any sort of question says resonance, you better have a double bond in there somewhere. Okay? You better have a double bond. So, when we get resonance, what happens is there's a double bond, but it's possible to put that double bond in more than one location. And what we found is that it actually does occur in more than one location. Remember, these electrons are not confined to a specific area. They can jump between these double bond possibilities. And it gives us resonance structures here on the top of 258. And it's NO3. Now, if we draw the Lewis structure for this, what we end up with is going to look something like that. Okay. Why did I put the double bond there? Because I could. Could I have put it there? Yeah. Could I have put it there? Yeah. So when you're asked to draw resonance structures, all you have to do, draw all the different possible places that you could put the double bond. Okay. And typically we're going to put arrows in between them. So if we put it up top, and then we also have one more over on this side. So we have 3 resonance structures because there are 3 different possibilities of where we can put the double bond. Okay. That's all resonance structures are. Multiple places where you can put the double bond. So if you ever read resonance in a homework or test problem, immediately you know we've got double bonds. Okay? We have at least one double bond, and there's multiple places that we can put it. What ends up actually being sort of true is, and I'll just take a moment, I didn't draw that this was technically an ion, okay? So I just want to point that out that I didn't do that, sorry. There's technically an extra electron here, but whatever. But what we found is that instead of the double bond being in one spot, it tends to spread out across everything. So instead of this being a double bond and these being 2 single bonds, really they all sort of end up being 1 1/3 bonds. Now you don't really need to understand why that is at this point. But that's why on the top of 258, they show 1 solid line and 1 dotted line. That is all, it's just indicating that in actuality, we don't see that there's a double bond and 2 single bonds. The extra pair of electrons sort of spreads itself out. So, and then the last thing here is another exception to the rules. Okay. And I know I'm going through this fast. It's because I want to spend more time on this on the next section that's coming up. Okay. Because that's where I want to focus today. Because, yeah, so I know I'm going fast. If you have questions, get in touch with me, okay? We'll make sure that we can get this to you. It's just, like I said, I want to focus on the next section. So don't stress right now if I'm kind of going fast. Anyway. The last thing in this first section, exceptions. There are some elements that are completely stable and happy without having 8 electrons. Some of them have less electrons, some of them have more electrons. Okay. One element that is very common for having less electrons is actually boron. Gives the example of boron trihydride. Okay. So if we look at boron, it's in group 13, so it has 3 electrons in its valence shell. And that actually is completely stable to pair up with 3 hydrogens. Okay. That is completely stable. it does not follow the octet rule. Okay. We also can have phosphorus pentachloride, where we have phosphorus attached to 5 chlorines. Once again, this is not the octet rule. There are 10 electrons there, but it's stable and happy. Okay. I want you to be aware that those exist. That being said, they are the exceptions. You should always try and get to 8 if you can. In fact, I'm going to go out on a limb and say, if the problem doesn't specifically say that it is not fulfilling the octet rule, don't try and make something that isn't. Okay?
Jackson Hinder, please come to the office. Jackson Hinder.
So, okay. There we go. So we got through that. That's what I wanted to get through quickly so we could focus on section 4. Okay. Actual shapes of molecules in 3 dimensions. Actual 3-dimensional shapes. We have something called the valence shell electron pair repulsion theory. The separ. And really what this is saying is that when a molecule arranges itself in 3 dimensions, it is going to spread these electrons out as much as possible because they're all negatively charged. They're all negatively charged and they want to spread out as much as possible. So we can take into account this when we determine what sort of 3-dimensional shape we're going to have. There are many different shapes, and these shapes all have specific bond angles, which we'll get to exactly what that means, and something called hybrid orbitals. A hybrid orbital is basically 2 orbitals that sort of smash together. We're going to mention hybrid orbitals for this, and then we're never going to talk about them again. Okay. So in order to figure out what the shape of a molecule is, we need to have the Lewis structure, because we need to know how many lone pair of electrons there are. That's actually 2 words, not 1 like I wrote it. And how many bonding pair we have. So bonding, obviously in a bond. Lone pair, like if we have this, that right there is the lone pair. It's not involved in any sort of bonding. Okay. So, question, how many bonding pair do we have in this molecule? How many bonding pairs of electrons? Well, how many bonds are there? 3. 1, 2, 3. So we have 3 bonding pairs. How many lone pair do we have? 1. This is the lone pair. We have that. So once you have that information, you go to the chart on page 263, and you find something that says it has 3 bonding pairs and 1 lone pair. That will then tell you what the shape is, what the hybrid orbital is, and what the bond angle is. Okay. So let's go through some of these, and then we'll do some practicing. Okay. If you have, and this chart also gives you just sort of a general example. So if you have something like beryllium chloride, okay. Actually this is beryllium dichloride, but it has two shared pairs or bonding pairs and no lone pairs. That is a linear molecule. Can you see why it's a linear molecule? Because it's in a line. Okay. Two pairs, two bonding pairs, no lone pairs. So then we get aluminum trichloride. That has the wonderful name of trigonal planar. Which looks like this. Okay. Planar because it's in a plane. They're all in the same plane. Trigonal, tri. Okay. So this has 3 shared pairs and no lone pairs. Okay. Oh, didn't mention the bond angle here, 180 degrees. Okay, 180 degrees. Bond angle here, 120 degrees between that.
I'm sorry.
Yes.
We have to leave right now.
Oh, for volleyball?
Yeah.
Okay. If we go to 4 shared pairs and no lone pair, we get this. This shape is very, very common once we get to organic chemistry. This one. This is tetrahedral. A tetrahedral. A tetrahedron is how you can spread 4 things out around a center atom as far as possible. The bond angle here is 109.5. 109.5 between all of these bonds. Okay, now this is the first one where we're going to have lone pair. Okay, so we have 3 shared pairs and 1 lone pair. This flat thing here represents a lone pair of electrons. So if we have 3 of them that are shared bonding electrons and 1 that is a lone pair, we get this that is trigonal pyramidal. Now it's very, very similar to our trigonal plane, but that extra lone pair pushes everything just a little bit because there is negative electrons in here, and so it pushes it down. So it's still trigonal, just like this, but it's pyramidal because it looks a little bit like a pyramid. It only pushes them down a little bit, but yeah. The bond angle here becomes 107.3. You don't need to memorize these, by the way. Okay? I will give you this chart, or at least a version of the chart. It may not look exactly like that one, but it'll have the same information. I'll give you that on a test. Look at this on homework and things like that. So, 3 shared, 1 lone, trigonal pyramidal. If we have 2 shared and 2 lone, this becomes.
Hey, there's been some interruption. Can we get the
This becomes what we call bent, which I think you can see why. We have these lone pair, which are pushing everything down. Okay, pushing everything down, so we get the bent molecule. This is 104.5. That's the bond angle there. Then the last two are kind of fun. The last two violate the octet rule. First one, trigonal bipyramidal. We have 5 shared pairs and no lone pairs. You can see there's a pyramid up here and a pyramid down here. Okay, so we have, it's basically like you've taken trigonal planar and you've added one on either side. Okay, so trigonal bipyramidal. We lost a few volleyball people already, so. Okay. And then this last one where we have actually 6 bonding pairs and no lone pairs. So this actually has 12 electrons in this valence shell. Basically, what you've done, you can think of it like a cube, and there's something on all 6 faces of the cube. We call this octahedral. So really what you need to be able to do is draw the Lewis structure and look at this chart and interpret it. So let's do some practice. Okay. We are going to look once again at phosphorus trihydride. So phosphorus trihydride. And it gives us some information. This is example problem 7 on 264, just in case you're wondering. Colorless gas produced with organic materials such as fish flesh rot. Okay. Interesting thing about phosphorus trihydride. It is, it has a common name of phosphine, which we actually have just recently discovered in the atmosphere of Venus. And so that is really interesting because on Earth, the only time we see this gas is when there is life present. So to find this gas on Venus kind of makes us think maybe there's very simple life on Venus. But who knows? Anyway, to figure out the shape, like we said, step number 1, we need to draw the Lewis structure. We need to draw the Lewis structure. So pH 3. As we said, if you have one thing with a bunch of hydrogens, that's going to be in the center. So really what we're looking at is something like this. Phosphorus, 5 plus 3, so we need a total of 8.
So 2 on the top, 2 top.
So yeah. So we have 2, 4, 6, 8 total electrons. So this is going to be our Lewis structure. All right. So now that we've established the Lewis structure, we can figure out the shape. Because we look at this and we see 1, 2, 3 shared or bonding pairs and 1 lone pair. So we go back to the chart and we find the one that has 3 shared and 1 lone, and it tells us that the shape is trigonal pyramidal, bond angle is 107.3 degrees, and the hybrid orbitals are sp3. Those are the questions that this asks. So let's do another one. More practice problems here. Once again, it's asking for the shape, the bond angle, and the hybrid orbitals. We get all of that from the chart. So if we do BF3, so BF3. Looking here, boron has 3. Fluorine actually has 7. But there's 3 of them, so that actually turns into 21. So in total, we have 24 electrons that we need to account for. Which means,
Wait, so use time 3, like 7 times 3.
yes,
Oh,
because there's 3 of them. So there's 12 pairs that we're actually going to be working with. Using kind of the same philosophy as the hydrogen, if you only have 1, there's a good chance it's going to be in the center. Not always, but it's a good starting point. So if we do this, okay. So if we put 3 bonds right there, so now we have 9 pairs left. Now we know that fluorine has lone pair around it. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've used up all our 24 electrons, and now we have our complete Lewis structure. Now I do want to point out, if you look at that chart, you will not see anything that says 9 lone pair. And the reason for that is we only care about what is next to the central atom. Okay? We don't care that these have a bunch of lone pair, because that isn't contributing to the shape. It's just what's here. So we look at this, we see 1, 2, 3 shared pairs, 3 bonds. And remember, boron is one that doesn't have to follow the octet rule. We don't have a shared pair. This only has 6 electrons there. So we have 3 shared pairs and 0 lone pairs. We go back to the chart, and 3 shared, 0 lone tells us the shape is trigonal planar. Our bond angle is 120 degrees, and the hybrid orbitals sp2. Let's try. Now let's just do the next one. OCl2. So oxygen, we look, has 6 electrons. Chlorine, they each have 7, so we have a total of 14. So we have a total of 20 electrons that we need, which means divided by 2 equals 10 pairs that we need to figure out what we're going to do. Once again, we only have 1 oxygen, so a good starting point is put that in the middle, see if you can make it work. Now, if we put 2 bonds right there, that takes up, well, 2, we have 8 left. So 1, 2, 3, 4, 5, 6, 7, 8. So we've used up all 20 electrons with our 10 pairs. 8 of them are all around the outside. 2 of them are there.
A lot of pairs.
So, when we need to find the shape, remember we only care about what's on this central atom. So how many bonding pairs are there next to this oxygen?
2.
2. And how many lone pair are there?
1, 2.
There's actually 2, so there's a lone pair there and a lone pair there. So if we have 2
It's going to be like
shared pairs,
this one, right? The one where
well, let's look at our chart. So if we have 2 lone pair and 2 shared pair, go down, we find it is bent. It looks like this. So lone pair, shared pair, right? And then just to finish out the things that it asks, the bond angle is 104.5, and the hybridization is sp3. Okay. So that's where we're going to finish up for today. Hopefully that makes sense. If it doesn't, I think I'll probably do a little bit of review on this because we lost some of the volleyball team here. And it is, you know, there's a lot of moving parts. And we went through a lot of stuff today. Anyway, so we're going to stop here, let you start on your homework. And yeah, like I said, as always, if you're confused about something, if you have questions, get in touch with me so that we can make sure that it gets resolved. There's that. This is
12. No, 10.
this is chapter 8.
I'm thinking of biology.
Yeah, biology is chapter 10. Okay, I'll let you get started on that. Yeah.